Dr. Ashley Montanaro has worked in this field for over 10 years. He's been specializing in quantum algorithms and quantum computational complexity. I had to read that as well. I'm sure he will explain exactly what that entails. He is extensively published in this space. He holds a PhD in quantum computing at the University of Bristol, where he is also working as a professor. He comes from a heavily academic background. However, what he's about to share with you is both accessible and immediately relevant. So please put your hands together and welcome Ashley to the stage.
So the first application I want to talk about is to do with power transmission, so electricity transmission. Now, in a country like Australia or the UK, power transmission suffers from a problem, which is about 5% of power is actually lost in transmission, just going through the power cables, the underground power lines, this kind of thing. And the reason for this is essentially electrical resistance in those power cables or those underground power lines. Now, a nice thing is that we know of materials that experience zero electrical resistance, which are superconductors. So why don't we use these for all of our power cables and underground power lines? Well, people have come up with experimental projects to do so, but there are some major challenges in working with these superconducting materials. In particular, they're hard to manufacture, and also they have to be operated at very low temperatures, so perhaps the temperature of liquid nitrogen or so. So this makes them expensive to utilize, especially for transmitting power over large distances. So, okay, maybe we can try and build better superconductors and to develop much more efficient low-loss power lines that way. Well, the problem is that the theory of superconductivity has been a long-standing and highly difficult technical challenge for theoretical physics. So, in particular, high-temperature superconductivity has been a long-standing open problem for many, many years, and is far from being fully understood. And the underlying reason for this is essentially this one I already mentioned, that simulating quantum mechanics using a classical computer is extremely inefficient. If we want to understand all of the quantum mechanical effects that are going to go on in a superconducting system, then probably the best way of doing this is building a quantum computer to do so. And in particular, it's believed that quantum computers could be able to simulate the Hubbard model, which is the theoretical model that's believed to underlie high-temperature superconductivity. And this could help us develop better superconductors, perhaps more easily manufacturable, or perhaps even room-temperature superconductors. And it could help us develop more advanced materials in other applications. For example, better solar cells, better magnets, better batteries, many different application areas here. And the next one I want to go into is quite different. And it's a different area. It's agriculture. We already heard David Riley mention this briefly earlier today. So modern agriculture, which is very high intensity and is supporting very large numbers of people, is essentially based around the use of fertilizer. We use fertilizer to enable us to cultivate far more crops than we could do otherwise. And in general, fertilizer is produced, or at least the ammonia in fertilizer is produced via a chemical process called the Haber process, or the Haber-Bosch process. This process has been credited with enabling the world population to grow by literally billions over the last century or so. So there are maybe many billions of people who are alive today who would not have been alive without this process. So it's extremely important. But there's a downside to it, which is that it uses vast amounts of energy. So this process, to use it, we need high temperature, about 450 degrees centigrade, and we need high pressure, so perhaps about 200 atmospheres of pressure. And because of this process has been estimated to consume 1 to 2% of the world's entire energy supply and 3 to 5% of the world's natural gas. So very important, but very costly. However, certain biological organisms, like certain blue-green algae and certain plants like clover, they use an enzyme called nitrogenase to solve this problem of producing ammonia much more efficiently. They can fix nitrogen from the atmosphere into a form that other plants can use, in this ammonia form. And so if we could understand how this process worked, we might be able to develop much more efficient processes for producing ammonia, producing fertilizer, and hence feeding more people or reducing our energy usage. However, the catch, as with the last application, is that we haven't been able to understand how to do this. The quantum mechanical effects that are going on in this reaction, in this nitrogenase, have defied our best classical methods until now. But it's believed that using quantum computers, we'll be able to simulate the processes involved in these chemical reactions, and we'll be able to understand what's going on and perhaps synthesize the required reaction steps ourselves and produce a fertilizer much more efficiently. The final application I'd like to discuss is a bit different. In this example, we have a quantum algorithm. In fact, we have a suite of quantum algorithms, but we don't know yet how good they're going to be. And the reason is, effectively, that the algorithms are too hard to analyze theoretically, and we're going to need to have large-scale quantum computers in front of us before we can try them out and we can see how well they actually work in practice. And the algorithms that I'm going to talk about now, they all fit within this general family, which are called variational quantum algorithms. In fact, in the previous talk, you saw one example of a variational quantum algorithm. And the way these algorithms work is they use a classical computer working in tandem with a quantum computer. So we have a quantum computer, shown in this picture here in the middle, which is a quantum computing experiment from IBM. And that quantum computer is used to produce certain quantum states, which are supposed to encode the solution to some particular problem, some hard problem to solve. And what we have is we have a classical computer as well, and the classical computer talks to the quantum computer and tells it to produce particular quantum states. So first, the classical computer dials up a particular quantum circuit on the quantum computer, and it says, OK, run that quantum circuit, and then we measure the quantum state at the end, and we see what answer we get. We see how good the answer is. And depending on how good the answer is, the classical computer then asks the quantum computer to dial up a different circuit and tries that one and sees how good the answer is now. And we repeat this process again and again, trying many different quantum circuits and using whatever classical optimization technique we like best to optimize over this space of quantum circuits to try and find the best quantum circuit for solving the particular problem that we care about. And the hope is that if we do this over a number of runs, we eventually get a good solution to the problem that we particularly want to solve. So on the slide here, on the right-hand side over here, we can see an illustration of one kind of problem we might try and solve in this way. So what this picture illustrates is a mathematical problem called max cut. And mathematically, the way this is defined is we have a graph, which is a connection of nodes together with edges between them. So these blue and orange blobs together with lines between them. And what we want to do is we want to assign a color to each of the nodes such that the smallest number of nodes possible that are connected to each other share the same color. So here you can see in this picture that there are a few nodes that are connected to each other that share the same color. But in general, this is a pretty good coloring. Most of the nodes connected to each other have different colors. And this mathematical problem can model a number of different tasks where we have some constraints that we want to satisfy. So, for example, you could imagine a problem to do with optimizing a telecommunications network, where maybe each of the nodes represents some communications device on your network. And it has a choice of one of two frequencies to communicate on. And two of the nodes are connected if they would interfere with each other if they had the same frequency that they were communicating on. So what we want to do is we want to assign colors or frequencies to the nodes to minimize the amount of interference in our network. So this can be modeled in this kind of max cut problem. But this problem, in fact, is an NP hard one. It's hard to solve classically optimally. We have some good theoretical evidence that this is true. And even if we don't think that we can necessarily solve it perfectly, efficiently with a quantum computer, we might be able to go beyond what we can do classically using such devices. We might be able to produce quantum states that let us sample from some distribution on these colorings of nodes, which is better in terms of giving us a good coloring more often than we can achieve with a classical computer. So I just want to finish by trying to highlight what I see as some of the opportunities and challenges for this NISQ era of quantum computing, like the 5 years' time kind of era of quantum computers. And the couple of challenges that we have, I think maybe many of you have already identified yourself, that firstly, the picture I had at the start of the talk about scaling up, maybe this is a bit optimistic. Maybe we won't scale up quite this quickly. Maybe we can't keep doubling our size of our quantum chips over the next few years. And if that's the case, maybe it will take a bit longer than 5 years to get to some of these exciting applications. Secondly, we don't know yet how well these quantum algorithms that I've introduced are going to perform in practice. We don't know if they really will achieve the complexity that our theoretical results suggest is the case. For example, near-term quantum computers are going to experience noise. We don't know yet how badly this noise is going to affect some of these algorithms and how well they'll perform in practice. So we're going to have to run the experiments to find out this answer. But I think this also highlights a real opportunity in this era of quantum computing that we're coming to next, which is that we're just now getting to the stage where we actually have these quantum computing devices in front of us, and we can try using them, and we can try to see what they can do and how well they perform. So what this means is that we're going to be inspired, I believe, to come up with all kinds of new applications that we haven't even thought of over the last 20+ years of quantum algorithms research. Once we have these things to play with, and once they're available to many more people around the world, it's my strong belief that we'll find out new applications that we could never even have considered before, because this has certainly been the case in other aspects of technology, and in particular in classical digital computing technology. So this is why I think the next 5 years is going to be an extremely exciting time for quantum computing research. Thank you all very much.